Visual Question Answering (VQA) seeks to provide responses to natural language questions given visual input. Recent research has focused on visual programmatic models (VPMs), which generate executable programs to answer questions through large language models (LLMs). However, VPMs often require long input prompts to provide the LLM with sufficient API usage details to generate relevant code. To address this limitation, AdaCoder is proposed, an adaptive prompt compression framework for VPMs. AdaCoder operates in two phases, a compression phase and an inference phase. In the compression phase, a set of compressed preprompts is generated, each depending on a specific question type, given a preprompt that describes all API definitions in the Python language with example snippets of code. In the inference phase, AdaCoder predicts the question type and chooses the corresponding compressed preprompt to generate code to answer the question. AdaCoder employs a single frozen LLM and predefined prompts, negating the necessity of additional training and maintaining adaptability across different powerful black box LLMs such as GPT and Claude. This is significant, as retraining or additional learning is not feasible for application to LLMs trained with huge data. In contrast to end-to-end learning models, such as GLIP, which do not explicitly distinguish between visual processing and reasoning, VPMs provide a more manageable and transparent inference process by generating executable programs specifically designed to answer questions. AdaCoder is proposed as a solution to reduce computational costs associated with long prompts in VPMs. By compressing input prompts, AdaCoder achieves high performance without requiring retraining or additional learning. Figure 1 illustrates the inference procedure of AdaCoder, where an adaptive programming instruction is used to generate a Python program for visual question answering. The effectiveness of AdaCoder is demonstrated by applying it to ViperGPT, reducing token length by 71.1% while maintaining or even improving the performance of visual question answering. The authors highlight the challenges faced by VPMs, including computational complexity, and argue that efficient neural network architectures require retraining or additional learning, which is not feasible for application to black box LLMs. Overall, AdaCoder is proposed as a novel solution to address the limitations of VPMs and improve their performance, providing a promising approach to reduce computational costs and improve the efficiency of VPMs. AdaCoder is a novel framework for adaptive prompt compression in visual programmatic models, VPMs, which generate programs to answer questions based on visual input. VPMs often require long input prompts, leading to computational expense. To address this, AdaCoder operates in two phases, compression and inference. In the compression phase, it generates a set of compressed preprompts, each tailored to a specific question type, given a preprompt that describes all API definitions in the Python language with example snippets of code. The inference phase adaptively selects a compressed prompt by classifying the question type and generates a Python program to answer the input question. Inspired by previous studies on prompt compression, such as LLM Lingua, AdaCoder is the first to propose adaptive prompt compression for VPMs. Notably, it is implemented with a single frozen large language model, LLM, allowing for implementation with black box LLMs. This work provides a comprehensive review of related work in visual question answering, VQA, and large language models, LLMs, covering the evolution of VQA models and the importance of interpretability in LLMs. The authors also discuss various prompting techniques that have improved interpretability, such as chain of thought prompting and tree of thought prompting, as well as previous work on prompt compression, including token reduction methods. However, they note that these methods are often proposed for small models and rely on fine-tuning or intermediate inference results. The contributions of this work are threefold: proposing AdaCoder, defining and formulating its procedures with a single frozen LLM, and demonstrating its effectiveness over the state-of-the-art ViperGPT model on 3 VQA datasets with GPT and Claude. The results show that AdaCoder reduces the token length of input prompts by 71.1% while maintaining or even improving question answering performance. Limitations include the assumption that the question type can be accurately classified, and future work includes exploring other question types and evaluating the effectiveness of AdaCoder on more diverse datasets. The AdaCoder framework is a novel approach for adaptive prompt compression in programmatic visual question answering, consisting of two phases: the compression phase and the inference phase. In the compression phase, a large language model, LLM, is utilized with two instructions to generate a set of compressed prompts, each specialized for a specific question type, by rewriting API definitions and writing code snippets. The inference phase adaptively selects a compressed preprompt to generate code for visual question answering. Unlike previous studies, which often rely on fine-tuning LLMs for specific tasks, the AdaCoder framework is designed to fully leverage the advantages of powerful black box LLMs without requiring comprehensive fine-tuning. The framework is formulated using a preliminary notation and settings, where an input image X and an input question Q are used to generate a code Z that returns the answer A. The code generation process is divided into two steps. The code generation step, which uses a code generation module Pi, often implemented using a single frozen LLM Pi, and the execution step, which uses an execution engine Lambda, a Python execution engine in this work. The preprompt definition is a crucial component of the framework, providing the LLM with detailed instructions on how to use APIs. The preprompt PPRE is defined as a structural aggregation of API definitions, coding instructions, and example snippets of code, and is used to generate code using image and text processing APIs. The adaptive prompt compression approach is expected to improve the efficiency and effectiveness of programmatic visual question answering. The notation and settings used in this work follow previous studies on visual question answering, where the input image X and input question Q are used to generate a code Z that returns the answer A. Equations 1, 4 define the code generation step, execution step, code generation module Pi, and preprompt PPRE, respectively. Figure 2 provides an overview of the AdaCoder framework, consisting of the compression phase and the inference phase. The limitations of this work include the assumption that questions, answers, and codes are in text form. Future work may involve extending the framework to handle non-text inputs and outputs, and incorporating more advanced techniques for prompt compression and code generation. The AdaCoder framework presents an adaptive prompt compression method for programmatic visual question answering, leveraging the GQA dataset, which encompasses 5 question types: existence of objects, category of objects, attributes of objects, relationships between subjects and/or objects, and global questions. The AdaCoder approach generates a code as Z equals pi ada, Q, with a total token length given by L, Q. Pi ada equals pdef plus pinst plus pcls plus cpi pcls plus q plus 2 q. Notably, while AdaCoder appears more computationally expensive than conventional code generation modules, it improves efficiency in practice when using black box LLMs such as GPT or Claude, due to significant input token length reduction. AdaCoder is shown to be more efficient and effective than previous prompt compression methods like LLM Lingua, as it can reduce token length while preserving code structure. This adaptiveness is crucial, as AdaCoder does not require additional training to compress the preprompt. Recent black box LLMs exhibit high zero-shot performance on text processing tasks, which AdaCoder leverages to enhance efficiency and reduce computational costs. The experimental settings involved 3 VQA datasets: GQA, VQA-V2, and NLVR2, with evaluation metrics including exact match accuracy, % for case-insensitive answers and reduction rate, % of input token length. Baselines include ViperGPT and LLM Lingua, with AdaCoder implemented on top of the official ViperGPT implementation. Implementation details include the use of GPT and Claude as LLMs, as well as an API set consisting of basic image and text processing functions. Experimental results demonstrate that AdaCoder reduces input token length by 71.1% while improving QA accuracy on all 3 datasets. The effectiveness and efficiency of the proposed prompt compression method are demonstrated, with AdaCoder outperforming the ViperGPT baseline and LLM Lingua. The results highlight the importance of preserving code structure during compression, as the simple compression setup that omits instruction prompt compression for specific question types significantly degrades QA accuracy. These findings emphasize the potential of AdaCoder to enhance the efficiency and effectiveness of visual question answering systems. AdaCoder is compared to other methods, including ViperGPT, LLM Lingua, and simple compression, in Table 2. The results show that AdaCoder outperforms these baseline methods in terms of accuracy and compression ratio. Specifically, AdaCoder achieves higher accuracy on the GQA, VQA-v2, and NLVR2 datasets, while reducing input token length and character count. The confusion matrix in Figure 5 reveals a question type classification accuracy of 58.1% on the GQA dataset, indicating that AdaCoder effectively classifies critical question types necessary for code generation. Table 3 analyzes the effect of question type classification on AdaCoder's performance, showing that using ground truth question types achieves the best performance. This highlights the importance of accurate question type classification, with a minimal performance drop due to classification errors. The instruction prompt RSPIN in EQ7 is crucial for compressing code snippets, increasing the probability of completing the program. Omitting this instruction and compressing prompts regardless of question type results in a loss of specific snippets necessary to complete the program, reducing QA accuracy. Table 4 summarizes the token length and compression performance for each component of the input preprompt, demonstrating significant compression of both API definitions and code snippets. The compression of API definitions effectively omits unnecessary descriptions and condenses remaining sections into shorter sentences. The computational time for experiments on the GQA dataset was reduced by 55%. Although a detailed analysis of computation times is not possible due to the lack of publicly available model weights and server congestion, the results suggest that AdaCoder can efficiently compress prompts while maintaining accuracy. The ablation study in Table 5 demonstrates that both compression of API definitions and code snippets contribute to reducing input token length and improving QA accuracy. Table 6 summarizes the QA accuracy obtained by using a single compressed prompt, showing that AdaCoder outperforms the baseline methods. Overall, the results demonstrate the effectiveness of AdaCoder in compressing prompts while maintaining accuracy. AdaCoder, a novel method for programmatic visual question answering, is evaluated through an ablation study to assess the effectiveness of prompt compression. The study examines the impact of compressing different input prompt components, including API definitions, code snippets, and instructions. The results, presented in Table 4, demonstrate a significant 71.7% reduction in token length. Furthermore, the authors investigate the importance of adaptation in improving QA accuracy while compressing input prompts. They find that using a single prompt of either adder or rel achieves comparable or slightly better performance than the ViperGPT baseline, while using a prompt of either obj or global significantly degrades QA accuracy. This highlights the importance of adaptation in improving QA accuracy. The authors conduct a comprehensive ablation study to evaluate the impact of different components of the prompt compression on QA accuracy, with results presented in Table 5. They find that compressing API definitions, code snippets, and instructions all contribute to improved QA accuracy. The effectiveness of using a single specialized prompt for different question types is also evaluated, with results presented in Table 6. The 4 compressed prompts specialized for obj, cat, adder, and rel perform the best for corresponding questions. A cross-question type evaluation, presented in Table 7, reveals that the prompts for adder and rel perform well across different question types, while the prompt for global performs poorly. This suggests that defining fine-grained QA types would be an interesting direction for future research. An error analysis, presented in Table 8, identifies the predominant type of error as wrong answers, with AdaCoder reducing their frequency. However, a 7.8% incidence of coding errors is still observed, indicating room for improvement in instructing large language models about API usage. Minor errors, including responses with unnecessary details, ignored instructions, and paraphrasing, highlight the need for further refinement in the AdaCoder method. This section provides a detailed evaluation of the AdaCoder method and its components, building on previous sections. The ablation studies and error analysis provide a comprehensive understanding of the method's strengths and limitations, highlighting directions for future research. The AdaCoder framework is demonstrated through qualitative examples of generated programs, showcasing its generalizability across various multimodal tasks. Figure 7 illustrates the adaptive prompt compression process, where input questions and images are paired with adaptively selected example code snippets, generating Python programs and intermediate outputs for question answering. Each compressed prompt consists of 3 or 4 snippets, with 2 shown. Error analysis in Table 8 compares AdaCoder and ViperGPT, revealing similar error rates across categories, except for wrong answers, where ViperGPT performs slightly better. Notably, AdaCoder achieves competitive accuracy across multimodal tasks, including visual grounding, counting, relative depth estimation, visual reasoning, image editing, and object tagging, as shown in Table 9. The framework significantly reduces token length while demonstrating consistent reduction rates, demonstrating its generalizability. AdaCoder employs a single black box large language model, LLM, for question type classification, textual compression, and code generation, eliminating additional training needs. The results show that AdaCoder efficiently generates programs for visual question answering by compressing and selecting prompts based on question type. While AdaCoder exhibits promising results, its limitations include potential issues when applying it to tasks beyond visual question answering. Future work may involve exploring more efficient and effective compression algorithms, investigating other LLMs, and evaluating AdaCoder on additional tasks and datasets. The AdaCoder framework leverages masked language modeling objectives for textual compression, contributing to its effectiveness and efficiency. This technical aspect is implicit in the framework's structure, particularly the LLM. The AdaCoder framework for adaptive prompt compression in programmatic visual question answering relies on black box large language models, limiting analysis from a neural network architecture perspective. Future research could explore alternative models, such as open-source whitebox models like Code Llama and StarCoder, which were unsuitable for prompt compression in this work due to their limited text classification and summarization capabilities. To advance multimodal automated programming, several future research directions are proposed. One direction involves developing methods for interactive code modification, enabling a more dynamic and responsive programming environment. Another direction is to explore the automatic extension of APIs, facilitating their evolution to become more efficient and effective in addressing complex requirements of multimodal interactions. From a long-term perspective, adaptively extracting necessary API definitions and coding examples will be critical in automating large-scale multimodal software development, reducing computational costs and saving energy. This could lead to significant advancements in the field, enabling more efficient and sustainable software development practices. The authors acknowledge the support provided by the JSPSKAKENHI grant numbers 21H04910 and 22K12089, recognizing the importance of funding in driving innovative research forward. I'm happy to help. However, I notice that the provided content to refine is incomplete. It seems that the original text is missing, and only a partial sentence is provided. To proceed, could you please provide the complete original text of the research paper or the transcript that needs to be refined? This will enable me to create a concise, technically accurate summary suitable for voiceover narration,